When looking at a substitution reaction, it's useful to decide whether an SN1 or SN2 mechanism will operate. And fortunately, when we compare the characteristics, that's pretty easy to sort out. Let me just outline the general aspects of each reaction, and then we'll look at their characteristics. The initial step of an SN1 reaction involves ionization. The leaving group leaves, carbocation is formed. In the second step, there's a reaction with the nucleophile. A pair of electrons to form a bond. The nucleophile can have from either side, so we may have two products. The SN2 reaction is different. It's a single step. Everything happens at once. We call that a concerted reaction. Nucleophile reacts with the substrate from the back side. Single product, inversion of configuration. And there we have it. Let's summarize the reaction mechanism characteristics for each. For the SN1 reaction, we're looking at a tertiary substrate, good to excellent leaving group, and anywhere from a weak to a strong nucleophile. A whole range of nucleophiles are possible, and a polar protic solvent. And if we change this to the SN2, what characteristics do we need to change? Well, the substrate is different, isn't it? We are going to be looking at methyl and primary substrates. We need to have good leaving groups, so good to excellent is fine. Weak nucleophiles are not good. Good to strong nucleophiles work. And as for the solvent, well, we have to have polar solvents, we know that, but aprotic solvents favor the reaction mechanism that's SN2. So there you have it. Where are the differences? Let's take a look. Well, the key difference is in the substrate for sure. Big deal. This has to have very little steric hindrance, and the tertiary has a lot. In both cases, we need good leaving groups, so that's fine. The SN1 reaction can work often does work with some very weak nucleophiles. But if there are strong nucleophiles, that's not out of the realm of possibility, but we need to have at least a good nucleophile for an SN2 reaction. And then another key thing is this is a protic solvent, and here we need aprotic solvents to favor the SN2. So those are the distinguishing things that really make them different. So now that we've got these reaction mechanism characteristics summarized, let's take a look at what that's telling us about how to favor an SN1 or an SN2 reaction. For the SN1 reaction, it's clear that tertiary substrates favor the mechanism, and if we want to really favor the SN1 reaction, we better have a very good leaving group. So we'll use an excellent leaving group. And if we want to really favor the SN1 reaction, we better use a weak nucleophile, because strong nucleophiles participate in the SN2 reaction, but weak ones don't. And clearly, if we want to favor an SN1 reaction, we'll use protic solvents, because they're not good for SN2 reaction. And what do we change for favoring the SN2 reaction? Well, the substrate substitution. We'll scale back on the leaving group. We still have to have a good leaving group, but it doesn't have to be particularly good, and so worse leaving group is a bit better. And of course, we're going to have a strong nucleophile, and the aprotic solvents will favor SN2. So you see that these factors that favor a particular mechanism follow directly and easily from four simple characteristics that we've learned about the mechanisms. And all we had to do was point to the special things that are really different about them, and we can favor one or the other. Now we've talked about tertiary substrates and methyl and primary substrates. It's fair to say that secondary substrates are likely to react by both mechanisms operating simultaneously. And we can affect the ratio of SN1 to SN2 by the leaving group, the nucleophile, and or the solvent for any particular substrate that we use. So there we have it. We've got a nutshell summary of these key factors. We know which ones favor which, and we know how to adjust the factors to favor one or the other. And we have to always recognize that if we're looking at a secondary substrate, we will expect both mechanisms to operate in some kind of ratio. Now I've got a second question for you. Suppose that we do believe that one mechanism or the other operates, or that a mixture operates. How do you know that? How can you tell? To answer the question whether the reaction mechanism is SN1 or SN2, there are two types of information you can look at. One is kinetics. Kinetics information easily distinguishes between the two. The SN1 reaction shows first order kinetics. The SN2 reaction, second order kinetics. That's where the SN1 number and SN2 number come from, first order kinetics and second order kinetics. And those two are easy to distinguish from each other. So if you can get kinetics data, which you usually can, you can determine whether it's a first order or a second order reaction, an SN1 or an SN2 reaction. The other type of information that helps a lot is stereochemistry. The SN1 reaction proceeds with racemization, as you see above. You get a pair of products, so you get a 50-50 mixture. So you start with an optically active compound. If it's optically pure, you'll still get a 50-50 mixture of enantiomers if it's an SN1 reaction. If it's an SN2 reaction, and you can observe the stereochemistry, it proceeds with inversion. And this is a complete inversion, so SN1 and SN2 are easily distinguished and quite different from each other, and they're measured using optical activity. For SN1, there will be no optical activity. And for SN2, enantiomeric excess equals 100%. So you can measure the optical activity, see where you are, and determine whether it was SN1, SN2, or you can actually calculate the relative amounts of SN1 or SN2. Because the enantiomeric excess, the measured optical activity, rotation, divided by the specific rotation. And for EE and percent, measure that by 100% at the end. And that percent value will let you determine just how much SN2 occurred. So there are two types of data that lets you tell whether it was an SN1 or SN2 reaction that occurred. Kinetics data and stereochemical data. They're relatively easy to obtain and lets you easily distinguish between the two, SN1 and SN2. So now you know which happens, how you know which happens, how you know how much of each. And of course, it's the secondary substrates where we're likely to be seeing mixtures of SN1 and SN2 reaction mechanisms. With the tertiary substrates, it will definitely be only SN1. And with the methyl and primary substrates, it will be definitely only SN2.